in our group, the 20, to totally the stuff, and then we have 15, something like this. PhD funding in the UK is necessary because we have tuition fees and all of this, so it's relative competitive. Yeah. Yes. We have nearly every year 10 fully funded students, and I have an advertisement at the end. Also for next academic year. So we in total Birmingham. So how many studies in my group? The moment it's one, it's Shaoqi, but it was 3. Yeah. Should we give it a go?
So good morning, everyone. Welcome to the Future Ocean Forum. I'm Jianping Li, Dean of the Academy of Future Ocean, AFO, at Ocean University of China, OUC. Today is our great honor to have Professor Gregor Leckebusch from the University of Birmingham. Let's warmly welcome. So prior to beginning, I'd like to take this moment to introduce him to you. Professor Gregor Leckebusch is a leading expert in natural science research on meteorological and climate. No problem. I think I read the climatological extreme events and the related impacts. His work is dedicated to natural variability and anthropogenic changes in extreme events like cyclones and storms and the relation to relevant risk assessments. Focus of his actual research is a better understanding of physical processes in the coupled climate system for the generation of extreme storms or precipitation and the assessment of predictability on different time scales of the on different time scales. He is UK Met Office Joint Chair and the lead author of the State of Climate chapter for the technical report of the 4th UK Climate Change Risk Assessment, CCRA4. It forms part of the independent assessment commissioned by the Climate Change Committee, CCC, for the UK. The theme of his talk today is Diagnostics of Extremes with Impact from Cyclonic Storms and Frontal Structures. So now let's warmly welcome Professor Leckebusch to give us a talk.
Good. Good morning, everybody. Many thanks for having me, and many thanks for welcoming me here in Qingdao. It's for me the first time, and beyond the introduction we got, and many thanks, Professor Ping, for this one. I'm German, and therefore I'm really excited to be in Qingdao because of your wonderful city's history as well. And I'm looking forward to this presentation probably as much as you do. And I try to keep it within 45 minutes. Perhaps I will be a little bit longer, but if you have questions, please just interrupt me, okay? Raise your hand, have a question at the moment you lose my content, okay? If you lose me, you have a question. If I don't come to the end, don't worry. At least we have clarified what I presented to you so far. So don't be shy, just have a question, okay? So what I'm trying to talk today about is a mix of different works we did in my group in Birmingham over the years. It's not one line goes through the whole presentation. We have 3 blocks in the end. So if you miss one block, there may be a chance to come back into the second block again. I have to thank a couple of people in my group, and foremost also Chauchi, which is in my group working in Birmingham, which is not on the slide. I have to apologize for this one, but that's a long list of people who I collaborated with over the past. So I will talk a little bit about why cyclones, and also talk about the Meiju front at some point during this presentation. I will give you a little bit of a flavor how objectively to identify extratropical cyclones and tropical cyclones. Then I will show you, and that's the main part of the presentation, some focus on how to apply these methods in a meaningful way. For example, the interdependency between tropical cyclone and extratropical cyclones, or Meiju extreme precipitation. And then at least, of course, I have one slide for you to take home a message. So just to set the scene a little bit, there are not only tropical cyclones out there. If you live in the mid-latitudes, you don't see tropical cyclones too much, but you see extratropical cyclones. And that's a picture from January 2014 in Aberystwyth, which is a city in Wales to the west coast of the British Isles. And if you can shut down the light, the first row, that would be great. Here is a person standing. And that's 2 meters, let's say. This person is 2 meters. Yeah, here is a person standing, and that's a 4-story house. And that's waves breaking on the shoreline in England or in Wales at this point by an extratropical cyclone. And you see all the debris here, obviously the smashing into the windows. So it's really something which we have to consider if you live in England. There's not only rain, there's also these windstorms which produce a lot of damage overall. And in this winter, that's a figure from the Environmental Agency. You see normally for flood risk, 3 types of warning. Yellow is already dangerous, and orange, and then red. And on this day, that was the most warnings ever issued. Red warnings, threat of life, in nearly all river basins on the west coast of England and Wales. So that's important. And when you see how this manifests then into damage, that's a road just at the coastline, completely destroyed. So it takes a couple of months to repair it. Obviously, you don't want to have these damages, but if you have then also a private property, you may have an insurance on your house against those damages. And this is the figures for 3 systems within the 2013-14 series. And you see here the affected regions: France, Great Britain, Germany, Denmark, and so on. And you see the figures of market loss. Market loss is a loss which the insurance company will pay to the person who had a loss. Let's say your private property is insured against loss, and that's for this system 1 billion euro. That's euro at this point. That's 700 million euro and 200 million euro for one event alone. Okay, so that's massive figures in terms of payments done by the insurance companies. They obviously would like to know how this works, and we as scientists as well. Yes, please. Yes, mostly as you see, let me go back. England is relatively small. It's only from here to here is some 600, 700 kilometers. So if a storm, an extratropical cyclone, which has a diameter of up to 2,000 kilometers, smashes into Europe, normally the whole of England, including Scotland, may be affected. And then northern France, Benelux, Germany, Denmark, Sweden, and so on. So the systems really track over this region. For this specific system, we had a lot of rain on the western side. There is some mountain range here, and all the western basins saw flood alarm. The eastern ones also, but not life-threatening. So the orography plays a little bit of a role, but also the system itself, it's highly dynamically in terms of where exactly the rain is coming. Good. please follow the example of your prof, okay? Have questions. We had this one when we go to 2021, that the whole series compares to Australian floods. So 2021 European windstorm series produced some 3,600 million euro damage in Europe. That's obviously a massive number, and people are really concerned about this. So we need basic research to understand how this goes. And a couple of years ago, we developed a so-called objective measure, the severity of these systems, because it's not easy to address the question, what is the severity? You have core pressure, you have wind, you have very heterogeneous wind field, not like tropical cyclones. And we identified an objective tracker as well as a metric to calculate the severity. And we calculate the severity above the local climatology. So we take the local climatology into account, and we use a 98th percentile based on a previous study to say once the wind speed is above the 98th percentile, then we would expect some loss. So we had this tracker created, and you see the wind footprint here, and you see the core of the wind field. And that's a little bit different than the core of the cyclone itself, as you know from tropical cyclones perhaps. That's the core, the minimum sea level pressure in blue. But on top of this now we have the wind track as well. And the pressure does not make any impact. That's not the point. The wind field creates the impact. So, and that's south of the extratropical cyclone core pressure as we would expect. But now we can quantify this in data, in model data, in seasonal hindcasts, seasonal forecast, decadal predictions, where we don't have an objective ground truth. Okay? And because it uses a percentile approach, we have automatically some kind of a bias correction in it. Okay? Good. We can do the same. And in the paper 2020, with my postdoc Daniel Beaufort at the time, we applied this method also to tropical cyclones. And that's an example for tropical typhoon Tip in 79. And we see the footprint again. We see the dots are the IB best track archive. And we see our SSI, where it was really, really intensive. We see how the wind footprint surrounds this piece, but we are not working with a fixed radius, because a fixed radius, basic assumption, Holland model or whatever, is not necessarily suitable. It's a good guess, but for an individual system, it may be better to use a different tracker or different approach, and that's what we suggest here. For this example, for example, if you look at Shanghai, it would be affected, and indeed it was affected from this system, although the 300 kilometer range would not have said. Good. So what we did in the first approach is we looked into IB tracks, best data. That's the climatological track density events per year. And if we only go to the most or the upper part of the distribution, so above STS level, you see this kind of a track density distribution. And with our V-track for the Japanese reanalysis 55 data set, we see more or less a very similar figure. We extend a little bit further to the east, but that's not really important for landfalling systems. But if you look at the landfalling systems, our V-track system gets the point, I would say. It's not perfect, but at least we have a good objective estimate what's going on. And then we can use this as a tool to assess, for example, hit rate. And this is the severity of a system in both figures. And that's the number of storms. And that's the number of time steps. The message is the same. The gray one is the best track data, how many systems you have in this period. And the black one is which one we identify in terms of with our V-track objective tracker, just using wind speed. And as we would expect, we only expect damage to a certain percentage for tropical disturbance, tropical storms, a little bit more. From STS level on, we expect good damage, and that's what we match in a certain way. We are not perfect, but none of these objective tracker is perfect. We can check this in respect to damage in million RMB here. That's million RMB, and that's a hit rate. So we don't get all the weak systems. We only have 60 or 70% hit rate for the weak ones, but that's fine. We can live with it. That's not the major animals making loss really significant. But as soon as we are above, let's say, 2.5 billion RMB, we get to 90% hit rate, which is good enough for our principal way of studying it in terms of understanding how this works in principle. So we have now we have an objective tracker. We have checked that the tracker has something to do with reality. And now we would like to answer two questions. What is the major source of uncertainty of understanding of extreme cyclones? One is obviously we have something which is natural variability, and we have something which is a short observation period, let's say 50-year or 30-year. So we cannot be sure that we have seen all possible extreme events in this 30 years. By chance, there may be not realizing the most extreme one. Yeah? We have different factors on different timescales which are leading to extremes. And then, of course, if you fit a statistical distribution like Pareto or something like this, these finite lengths of time will obviously create uncertainties in the estimate of return periods, especially for the tail events in this distribution, so the 1 in 50 years, 1 in 100 years. If you only have 30 years of data, it's very, very difficult to estimate the 100-year return period. It's pure estimate. The error bars are massive. And these two things we try to solve in an approach we developed 2016 in collaboration with Munich Re at the time, and we call it the Olszynski approach or pure ensemble event set. We use forecasted events, and that is now very odd perhaps, which did not realize. So in the end, we use all the wrong forecasts, okay? Forecasts are all the time a little bit wrong. But from the point of view, you are sitting on a forecast, you're riding with a storm, you don't know that you are wrong. You are physically exactly the same animal as the piece which is very close to reality. So what we do with this approach, we try to do this for different data sets, of course, but we try to understand how this can be used better in the assessment of the risk of occurrence. So windstorms are rare. I showed you this already. These are individual numbers for specific events. And what common data set give you maximum, if you really maximum, 50 to 100 years, perhaps less. What industry is doing at the moment is using stochastic event sets. So they take the historic observations, have 50, 60, 100 events, and then stochastically they change those tracks with random walk or other mechanism to create new tracks. This track, for example, goes into North Canada. This is all over Greenland. So stochastically you can create those tracks. But they are not linked physically to each other anymore. They are not physically linked in itself. So it does not mean they could happen in reality. Statistically, they can occur, but whether they would happen in reality and whether they are physically consistent is a different question. So with our approach, what we are doing is we use ensemble predictions from, for example, hindcast, seasonal hindcast, decadal hindcast, whatever you want. And for example, if you look at ECMWF system 4, you have 51 members times 32 years, which roughly gives you 1,500 years. Not 30 years, but 1,500 years of physically realistic, possible events. And that's exactly what we are looking for. We'll try to understand how the ability of occurrence would be if you have more years of the same climate. Okay? So that's in reality a 50 ensemble member. Here you would see a storm. Here you would see not a storm, and so on. So you can really identify them, but automatically, of course. Otherwise, you would take ages and years to do this, to get something in terms of understanding how it works. So we apply this setting to the question, of course, how global perils may be related. So that's a study from Lloyd's with the UK Met Office in 2016, so some 10 years ago. They followed this figure in how far risk at certain regions are related to each other. And one famous risk is obviously the link between European windstorms and the North Atlantic hurricane season. And we looked at this in a view together with our cooperation partner at the time, and how far is the Atlantic hurricane season and the European windstorm season depending or independent or not independent from each other, and whether there's a pathway which exists between the two through a climate teleconnection. And what we did is, of course, we address the question of data limitation. So when you do, for the high quality error, the correlation between tropical cyclone occurrence and extratropical, you end up with a correlation of 0.2. So they are not correlated, more or less. So that's common thinking. And that's for insurance companies quite good, especially for reinsurance companies, because they can assume they're independent. You don't want to have a loss here and a loss here underwritten at the same time. That's not what you want. So the question is then, can we build an event set from these ensemble prediction system, which is large enough perhaps to identify what the real relationship between those two target areas would be. So we used EPS CES5 from ECMWF, 51 member, 36 years, initialized on the first of each month, lead time 7 months. So we have the peak of the hurricane season in it. We have the peak of the European windstorm season in it. And it's relatively high resolution, 35 kilometers. So we assume we make not too many mistakes with respect to this. So if these two would be independent, and you would go for a hurricane season top 10% or top 90%, that would be your probability. Then if you go for European windstorm season, top 10%, bottom 90%, bottom 10%, bottom 90%, you wouldn't end up in these probabilities. So a top 10% event here, a top 10% here would have a 1 in 100 probability. Okay. If you are in the bottom 90%, you would have an 81 in 100 probability to get this. That's if they would be independent. Okay. So we did this for one specific parameter, our seasonal storm severity index. So we accumulated over all events we have in these data sets, which affect the region of England and are then as well as a hurricane season. So this figure gives you, this figure gives you the Atlantic hurricane season intensity. So weak here, strong here. This gives you the European windstorm season, weak here, strong there. And the figure shows you in color the percentage difference from predicted numbers of seasons. So the predicted numbers of season are the independent numbers of season, what I just explained. And what you see here, if there's a very strong European windstorm season, very strong hurricane season, they are negatively linked to each other. So there's less a probability. It means in the year where you have a very strong TC season in the North Atlantic, you have a higher probability by 40, 50, 60% to get a weaker extratropical cyclone season. That's good news for insurance, for example. But we can quantify. It's not independent. You see clearly how this links across a different sector as more extreme the season gets. And we said, okay, that's one information. We are happy to have this information, but how does it work? What is the background of this one? So we checked the, checked the bottom 5% years, so 92 years, with the largest hurricane to windstorm intensity difference from August to October to December, so from late summer into winter. And what you clearly see, that's the SST anomaly in Kelvin. You see this La Niña piece of a tongue in the Central Pacific, which is characteristic for all of those seasons where this difference is very large. We were quite surprised when we saw this. So when you think about the next step, how does this manifest into a teleconnection? We show here these years with low tropical cyclone, high extratropical cyclone, December, January configuration. And what you see is from the tropical Pacific, you see this negative anomaly spreading into the North Atlantic. And for high TC, low ETC is just the opposite. Blue means you have a reduction of the geopotential height. That's 700 hectopascal geopotential height. And it means you create a wave train which reduces over England, that's just, here on the zero line, a negative geopotential high in these high ETC years and a positive geopotential high, obviously leading to low ETC years, reducing geopotential or pressure gradients over the European sector. So you create an information from Central Pacific via North America into Europe, and to link these two connections, not directly the hurricane is interesting for the extratropical cyclone, but they have a common underlying factor influencing both in an opposing way. So that's, you cannot do with reanalysis only, because the data set would not be long enough to create this information. So another one, and we come here to impact, is we looked at the West Pacific parametric typhoon insurance approach. And that's a collaboration we did with Swiss Re in Beijing at the time, just before COVID and over COVID. So in parametric insurance, just to repeat the concept, you have a payout of insurance that's only triggered when a certain threshold, a trigger point, is surpassed. So in normal property insurance, you have to prove to your company where you have the insurance that there is a loss. You have to have a proof of loss, otherwise you don't get money. Okay? For parametric insurance, that's not necessary. You get the money as soon as one threshold is exceeded. And the idea is that's much faster than normal insurance because you have no administrative law or less administrative work, no physical damage assessment, and especially in disaster risk and reduction applications, that it's a nice tool to recover quickly. And for example, in China, Guangdong province government issued these kind of contracts or asked for these kind of contracts from reinsurance companies to bid in. And that's the background why we did this. So the point is that at the point where we did this, trigger points were depending on CMA TC tracks. So that was a ground truth. You need to have some ground truth. Otherwise, you cannot say, is it a loss or not a loss? And you need station data, wind speed, to be selected in this area at the right point to be objectively representative of the wind climate at this point and in how far it would link to damage. So the point is that at some instances you will see is a storm really particular circle or in distance to a location? And I showed you with our footprint approach, we get this more highly variable than just a fixed 300 kilometer red circle. So one system may approach the region, and that's the Great Bay Area here, and just being off the circle, but the wind field may still approach. But the first condition, the track is in a circle, is not fulfilled, so no payment. So that's obviously, in the end, leading to the fact that trigger points are not consistently triggered. And that's not good for a parametric insurance product, because that would increase inequality, and it's not fit for purpose at this point. So we checked how far can we go and build a suitable trigger for parametric insurance using our approach. And we obviously will have limited observed data. So we go back to the EPS-based event set, and we do this for typhoons in the West Pacific. And of course, we have some question to solve over our undercompensation. We would like to get this right, the trigger right. And sorry that the slide is cut off here. We do not address, so therefore it's probably not important to be on the slide, the basic risk question. So when you issue these insurance, you have to have a basic risk. You have a certain wind speed, you don't get payment at all. That's called the basic risk. We didn't go to the basic risk discussion. What is a tolerable basic risk? Okay, that's more a political, ethical, societal question to solve. So when we do this, we used, again, non-realized but forecasted ensemble events. And here we use, sorry, you cannot see anything. I put myself here. We use the TORPEX interactive Grand Global Ensemble called TIGE. That's an operational archive of 10 to 15-day forecasts from leading forecast operational, like CMA, ANSEP, Meteo France, DWD, UK Met Office, and so on. We track objectively TC event sets, TCs, and then we can robustly estimate what the impact would be. And if you do this, that's a little bit of information which data we used, CMA, ECMWF, JMA, Japanese, and ANSEP, with the respective members and lead time. And we did this for only 10 years. At the time, there was not too many data available at the time. Now we could do this and repeat it again. And what we do here, we have, of course, our tracking with B4 et al. We remove ETCs and disturbances. We have a logistic regression classifier in it. And we remove those systems which are initialized. But the core is to understand that's Typhoon Fito, and that's in black. Hopefully you can see this, the real track. And these are all different siblings of Fito. So Fito hitting south of Japan is very different from Fito hitting the Philippines. But we can use these different forecasts and say we try to make sense out of it. So what we do, we track objectively in Japanese reanalysis 55 for the 1979 to 2070 period. These would be the genesis points of tropical cyclones, of typhoons in this region. This would be the landfall, roughly 100 pieces along the coast of southern China, and Guangdong province is here. And the black arrows shows you areas where you didn't have a landfall in these 30 years. So it would be very, very difficult to say anything about a return period impact for these regions without having a landfall in the observed record. If we go to TIGE, you see these are all the genesis points of cyclones we could consider. And if you go to numbers, from 100 we go to 11,000. So we have 11,000 physically consistent tropical cyclones with impact potential to study. This means you can also do ENSO-related stuff, Indian Ocean Dipole-related stuff, and so on. We didn't do this in this study, but all of these questions can be addressed as the example before. So then you get a very different distribution, or not different distribution, similar, but filled with events, which you then can use to do assessment of return periods or return levels. And this is what we did for this study with RIS3, Beijing, and I don't go into the details, but in the end, we validated with observational data. So in blue dot would be our ensemble-based approach. In red would be observed, and these are different stations. I have to apologize, you cannot read the names. I cannot read the names either. That would be for a 20-year return level, wind speed 30 meters in this station, 20 meters at this station, and so on. So And then we get different error estimates and different values. And if we then put this in an extreme value distribution to fit, for example, return levels, return periods, you would see this is a black line for Bayun International or Boran International. And the gray line, if you can see them from behind, would be the estimate if you use the observed values. And the blue line would be the estimates. We did a percentile match here that they look comparable. So you can have information of a 50-year or 100-year return period at this station to be 20-21 meters, for example. And that's very useful information because you can check whether your observations are reflective of this general climatological background or not. You don't have to use this, but you get a feeling how wrong or how reflective, how representative your station data at this point would be. Good. So good so far. Any questions to this approach, quantifying, understanding what the dynamics is to a certain degree, and then have a better picture of occurrence frequencies? Yes, please.
The reasons they didn't get realized exist in the broader climate setting that, like, I don't know how that's, I mean, for this case, it's valid, obviously, but like for like ENSO or whatever, it doesn't make sense to you.
Makes sense because in these 15 years or 10 years of forecasts, all these forecasts are initialized with this current climate. So 0 UTC or 12 UTC is the best forecast data you have. So if you are an ENSO positive or ENSO negative, it's fully reflected. So it's real data. The initialization for these 15 days is synoptic meteorology. It's the same initialization. And then you check which TCs happen in this course. We throw away the first couple of days so that we have pure event sets in it. But there's a probability of a TC because the environmental conditions are within these 10 days triggered and initialized every day. Yeah? So you are within the specific ENSO phase. You don't change the ENSO phase. If you are an ENSO positive, you still are an ENSO positive. It's 10-day forecast.
To change it. Okay, thank you.
Good question. Yes?
During your analysis, you have used more models and theories. Now I was wondering to know which the best model do you use in your life for detecting a cyclone storm, and also the theory you used to manage that such kind of models. Yeah.
Yeah, so very valid question. And I think we discussed it yesterday. Yes, we could have checked in how far the CMA model compares to the Japanese or ECMWF or NCEP in terms of skill for the next 10, 14 days. We didn't do this because skill is not what we are after. We are at those events which are forecasted but did not realize. So skill would be, if the forecast would be perfect for 15 days, there would be no other hurricane or TC typhoon than the realized one. But this figure shows you that's not the case. Yeah? These are the 10 days forecast for the same system. So we didn't check whether CMA would be here and Japanese areas would be here. So we didn't check this because we put everything into one ensemble. So we don't here we are not after model biases. We are after the full ensemble. Yes, you're right. We could have checked that one model suite would be forecasting typhoons better than the other. But that's a job for the operational guys. Yeah? They do this and they know that in certain instances ECMWF is very, very good. In other instances, this model is better and so on. So we, in this approach, we don't go for skill. We go for climatological behavior and therefore then study the underlying physical factors. Okay. Say again.
Number 5. Yeah, slide number 5.
Slide number 5.
Yeah.
Slide number 5.
Yeah.
Okay. Oh, sorry. Slide number 5. Takes me a time. Sorry.
Yeah, it's
We get there. Don't worry, we get there. So that's slide number 5.
maybe it's 6.
6.
Next down.
This one. Sorry. Yeah. Yeah.
It's the slide who showed the strong cyclone on the west part and weak strong on the east part.
I'm not quite sure what you're after.
Yeah.
You mean this one?
Yeah.
Okay. This?
Is this one or this one?
Okay.
Yeah.
Okay. Yeah. Okay. Yeah.
Yeah.
Good. That's a
Yeah.
snapshot of one day.
Yeah.
One day in the UK during one of those storms. Okay. And it gives you the from the environmental issues for the people. Don't go to this stream. It's a threat of life because it can rapidly have more water than normally. So discharge included.
Yeah. Compared to these graphs and the field we ran aft, we found that on the west part, the storm are too strong, and the east part, if you look, you find that on the east part, northeast part, there is a strong storm too.
Yeah, but that's
Yeah.
that's one day. Okay.
Yeah,
What's-
that's why I was wondering to know what happened on the northeast part, because
Okay.
compared to other parts, the storm are weak. So
First answer is have a storm approaching from the west to the east, and there's mountain range. You have more precipitation on the western side. And these are flood warnings. It's not rain warning. Flood warning, it needs a stream, it needs a river as well. And there are more rivers on the western side going into the Irish Sea in the west than to the North Sea. The North Sea, they are shorter, and therefore the water is less accumulated. The catchment areas are smaller, and there is less rain. That would be my explanation for this specific figure at this specific day. Okay? It's not a climatological figure, it's one day. Okay? Good. Any more questions? Okay, then I will jump forward. We change setting. We go to really less specific now, not only for TCs, but also for other extremes. And one of those extreme trigger of precipitation is obviously the Meiju front. And you all know the Meiju front. You're better familiar with this than I, hopefully. And it means that if you would like to understand how future extreme precipitation in China, for example, in the Yangtze River basin would unfold, you would have to ask yourself, how good are climate models in producing those Meiju front structures going forward in time? So you validate those first. And we did study to check and how far we can develop suitable tools for climate services to predict extreme regional rainfall. I'm not talking all of China, I'm talking regional rainfall with confidence. So what do we know about the quality of those CMIP6 models, for example, to model the Meiju front correctly? And so it's a nice picture here of the Meiju front. You see these convergence bend, and normally you classify this via the equivalent potential temperature 850. And then you would have a good proxy, and you have to do a little bit more, but it's important. Yeah? When you see 45% over the lower middle Yangtze River from the Meiju front, record-breaking extreme Meiju rainfall in 2020, a lot of loss, unfortunately, fatalities. So you have to think, what is the representation of the Meiju front in models? If you only go for a grid cell and calculate precip, it will not necessarily tell you the correct story. So that's for a data source from China, CN05.1 data source we use at ground truth to understand what the real precipitation is. And to cut a long story short, these are 38 CMIP6 models. And unfortunately, the quality of the figure is not very good. But that's one model, that's another model, and so on. This one is a multi-model mean, and this one is the era 5 ground truth in this sense. First message, look at the different models. Look at this one. Over position of the Meiju front in the north, or underestimation in the south. This one is just the opposite. Underestimation in the north, overestimation in the south. And if I could read the figure, about 50 to 60% under and overestimation. Okay, so that means in half of the time, the model makes a major front at the wrong position. Zoom in a little bit, and again, sorry for the color scheme here, that's not optimal. That's again this tiny little picture we saw before. This is where in June, and that's only for June, the major front normally is detected up to the detection probability. This is a model bias, a multi-model bias. Okay, all models putting together, calculate the difference. You see in the area where the major front should be, a significant underestimation, and then further north and further south, overestimation. So in reality, it's smeared around. Yeah, it's just somewhere. Okay, in the multi-model perspective. So that's not helpful. Okay, that's also not very confident. We check then a little bit more closely how we can understand what's going on. And then we have May, June, July, August. So we follow the system over the season. And we nicely separated red and blue group of models. And here you see the center of action. We define it as the highest track density. Longitudinal bias or anomaly and latitudinal bias anomaly. So that's 5 degrees too far north. That's 5 degrees too far east. Okay. So, and if you do this with the red and the blue models, it doesn't matter which model is what. Yeah? So that's for the next question. But if you do this, we can see this systematic behavior. The blue ones start with a large north-south bias. Then over the season, May, June, July, August, it corrects itself a little bit, or they're correcting. And then in August, they are more or less there where they should be. The red group, although, start off with 3 degrees east. 3 degree east center of action is very, very large. Corrects a northeast, northwest, north-south bias to June, but increases the east-west bias. So in August for the red group, you are 5 to 6 degrees far east, which means the extreme precip is not falling over land anymore, it's falling over the ocean. The system itself produces the same amount of water, same amount of precipitation, perhaps, but it's at the wrong place. So if you use these red models, for example, for some kind of a future adaptation and climate change study, you will be misled because this bias will still be in the model. Okay? And that's not to be happened or corrected with the grid point bias correction only, because that would work on one grid cell. But this one is a more systematic structural mistake in the model to create a synoptic structure at scale, which creates regional extreme precip. Good. Oh, sorry. We dig a little bit deeper in terms of understanding where this westward or eastward bias came from. Because of time, I will not go too much into the detail, but what you see is here the composite 850 hectopascal anomalies in color, so that's geopotential meters. And the westward bias models are characterized by a north and westward extension of the subtropical high, and the eastward bias a reduction of the geopotential height 500 over the western North Pacific region. So the models obviously do not get the mass distribution correct. Too much mass in the North Pacific high, extending wrongly westward into the area where it matters for the Meiji to be created. So they create them too early over the ocean or too late in the season in the region where it matters. And that's relevant because you have vegetation, you have the background climatology, and then if the extreme precip is wrong in this background climatology, you may be very misled for future statements of change, perhaps. Good. We can still try to get a little bit of a correction understanding what's going on. And now we focus on extreme precip on a grid scale, and that's hopefully the area where adaptation measures will be done. And we say we use an approach which we call, or is called causal inference, and we use large-scale modes like ENSO or the position extent of western North Pacific high or the Indian monsoon in a causal inference approach to find the best driver of this. And we use over 20 of these large-scale modes in this approach as more as possible. It's a semi-AI piece, if you'd like to say so. And then we use these large-scale modes to predict statistically to build a causality-guided statistical model to use this as output extreme rainfall. So this would be our predictor, predictant, and this would be our predictors. So we cut out the extreme precip from the model. We don't look at it. We just look at the large-scale modes and build a transfer function from these large-scale modes to extreme precip in one grid cell. And we extreme, again, it's above the 95th percentile. And we have, of course, the Meiju front as well in it. We only take the rain from the Meiju front in this application, and then we check in how far the large-scale modes can explain and can build a statistically predicting model, not predicting time, statistically predicting model for extreme precip. And if we do this, you may remember how the ground truth is looking like, the extreme precip in this black box, yeah? A couple of slides ago. This would be the half-monthly model we built. This is the monthly model, and this is the RMSE, so the error of this one. And you see the half-monthly model is much better than the monthly model. So let's continue with the half-monthly model. So it's 15 days time period. So this black line gives you the observation of the extreme Meiju precipitation, and that's the annual mean of the extreme. Sorry for the naming here. The black line would be the observed value, and the blue and the red line would be our modeled value. And that only takes into account from era 5 large-scale climate modes. No information about regional precip included, just the large-scale modes from era 5. So we conclude that we have a model, we can build a causally guided statistical model on a half-monthly basis, which better performs the monthly one, and it shows a large annual perspective degree to coherency to observed one. So we were very surprised that that's possible. And then we checked that that's not by chance. And what we did here, we plotted the top frequently chosen predictors in the half-monthly model for the second half of June. So that's only for the second half of June. This one is the IMI, the Indian Monsoon Index, which obviously acts relevantly on the northern side and on the southern side of the Meiju. This is a Silk Road pattern with a lag 3, so 40 days before, which obviously influences strongly on the extreme precip on the northern side in mid-June, or the South Asian high, which is more reflective on the southern side. And we look for these coherencies on the grid cells to be sure that this factor is not randomly chosen. So what we don't want to see is a carpet of different predictors on these maps. So although it's a complete or semi-AI piece, we have selected obviously relevant factors and identified relevant factors which were perhaps not in this clarity identified before for explaining extreme precip on a daily basis. We can apply this now to CMIP6 simulations, and that's for the historicals. So a model validation for June again. This is the observed value. And this is what 4 models we just picked randomly for do with direct precipitation. And that's obviously not too good. It's completely different. Yeah? So the model itself creates a precipitation. Yeah, okay, that may be right, may not right. We say we can do better. We apply our causality-guided statistical model to it, and we can produce out of this model something which looks more like the reality. So we have, in this sense, a bias correction which is built on the large-scale understanding of influence of extreme regional precipitation. But we did one more thing. We checked in how far, if we build such a model, we would build it for different PDO phases differently. So is the question to be answered that, for example, Ding et al. Published a shift in precipitation pattern around 1980, coincidentally with a PDO change. So if this is really true, then our model may react differently if we change it per PDO phase. And we did this and checked it. And what we did is, this is the all model. And again, it's the, this is a Pearson correlation. So red is good, blue is bad. All model, so the model for all years, independent of the PDO phase. This one is the model for PDO phase negative only, and this for PDO phase positive only. And you see we increase the number of red dots in there significantly. What it means is, in the PDO phase plus or negative, we build different models. We have different large-scale drivers driving extreme precip. That means if you build one model, if you have one view, this influencing factor is influencing extreme precip all the time like this, that's wrong. That's non-stationary. We have different predictors in different years depending on the PDO phase. In other words, our model per PDO phase is better than the overall model. And that's interesting because if you think future climate change, you would have to think natural variability mode as well on top of the climate change signal to get a real estimate of potential extreme future precip. We did a third test. We applied this to decadal hindcasts. So we wanted to see whether this method, just focusing on the large scale mode, would give us a better decadal prediction than if you just take the model raw output and precip. And it does. So the blue line is our approach. The dotted line is in this case, DEPRI system 4 direct output. So in May, you have an RMS of 2 to 3 millimeters per day. In June, it gets 3.2, but we are still better. And even in August, where you have less precip, we are better. So this model obviously improves decadal prediction of extreme precip in the Yangtze River Basin. That's not uninteresting because it can be used, for example, for long-term management of the Three Gorges Dam or something else. Good. I'm with the conclusion. I think I'm good in time. Okay. I showed you. Sorry. I showed you something about the diagnostic of relevant extremes, hurricane, typhoons, extratropical cyclones. We can show that if you use this approach, then the hurricane and extratropical windstorm season are not independent. They have common causes of similar, or not similar, but opposing variability. We could use an approach to develop suitable triggers for parametric typhoon insurance. That's a really practical application. We can, beyond this, do studies on global climate model performance for extremes, for CMIP models, CMIP6 models, for example, where we would have diagnosed that some of them cannot really reproduce the MEE front characteristics, which gives you large uncertainty for rainfall. And we developed successfully a method to correct for this in a certain sense and create useful information for May-June extreme precip, improve decadal predictions. And that's a couple of pieces of literature, just if you are interested and cannot sleep in the evening, then you can read it. You will fall to sleep very quickly. And last but not least, I advertise the University of Birmingham. We are the second city in England. We only have 1.2 million people, so we are not comparable with your dimensions. But we are the second city. We have obviously this year again 10 joint funded PhD scholarships in collaboration with CSC to start in autumn 26, so next academic year. So we would be happy to see a lot of applications. And if you are interested to do a PhD, for example, in the United Kingdom with me or with colleagues, feel free to contact colleagues in Birmingham or myself. And then we will guide you through the process. And I think the first deadline is somewhere in January or March or something like this. You know this better than I for CSC. But please, don't be shy. Give it a try. If you would get rejected, nothing has happened. So if you don't get rejected, something will happen. In this sense, many, many thanks for your attention. Many thanks.
Okay, thank you very much for your excellent talk, which covers two aspects, yeah, at least. So I think you guys will have a lot of questions or comments. Please do not. Yeah, go ahead. You understand?
I'd like to ask you how your opinion of the high resolution simulation to typhoon forecasting, like coupling CFD and WRF, so we can improve the modeling. What's your opinion?
Yes, absolutely. When you talk forecasting, high resolution is the key to a certain degree because you will have or would like to have the forecast. WRF is one way to do it. Limited area models you can use. Yes, you don't have to do, but WRF is good. So global scale model simulations on 3 or 5 kilometer, which obviously is very expensive and takes very long to run, but they are available. I cannot comment with full certainty, but partly they are, in a lot of instances, they are good and better than the old climate model version because they can directly solve convective permitting simulation. It's very, very important. This question is beyond what I presented because this tracker, for example, only uses one level of wind. Of course, this level of wind may be biased, maybe not high enough, but therefore we use a 98th percentile. We build it back to the climatology of this model version. So this can also be used in high resolution models. Yes, we built it at a time where high resolution 3 kilometer was not possible. So, but still we want to have information about 50 members, 100 years, and that's still not possible with convective permitting models at the time. We don't have so many runs. You still have one realization only. The whole idea is here to get more realizations which are physically consistent and are representative of this climate as a positive and so negative even the MJO would be on the face, if you would like to say so. Yeah? The point is, we could retreat this with convective permitting models if there would be enough members. Otherwise, we have the same reality, and we don't see anything changing in the robustness of our estimates of return periods. You're welcome.
Yeah, find the second part. The last part is super, because that's exactly forcing my warehouse.
Okay.
Yeah.
Good.
Large-scale dynamics, teleconnections, so on and so forth. A question, a little bit technical.
Yeah.
You build this causal framework, right? Using large-scale patterns. Just wondering if one question is how many modes to keep. That's one. Second would be if there are no biases, right, between models and observation, how do you do the correction?
That's it. Okay, let me answer the second question first. We did not correct the large-scale modes. We take the large-scale modes as they come from the model. We know some models, for example, cannot do the NAO correctly. NAO is shifted a bit to east, to north. We said, okay, but we stay simple. We don't know this before. We take the model out, but we assume I'm a practitioner. I don't know this. I take the model from the archive and do it. If we take the raw NAO or Silk Road pattern or whatever, and then build a statistical model, we still get it right. And that's astonishing. We are not perfect. We are far off perfect. Potentially we are not perfect because the large-scale modes are not perfect. And there may be an influence along the process chain. But we are still better than just taking the raw precip from the model. But we find a useful one. If you take one model, bias correct everything, as far as we know, you would potentially be even better. But then to do this for 38 models, for all the modes we put in, that was work of 1 year within a project. Then probably would still working on it. So let's say it's a mix between availability, efficiency, and time. But you are right. The next step would be the assumption would be if we would bias correct all the modes, put them in, would be better. But the assumption is then that these are the only factors contributing to it and contributing major to it. And the bias correction is correct, which is difficult for long-term variability modes, PDO, for example. Georgi had shown that if you take the PDO 100 years back in time, it's very different influence. Of course, you would also build in, or you would have to build in the different link between PDO and extreme precip as we did. In the first version, we didn't do this. But that would be the next elevation step. So exactly what you say, plus the next different models for different time slices, that would be the holy grail. Yes. First question was about the technicality and which modes we did select. I had a slide, but I deleted it. It's over 20 modes we picked. For the Silk Road pattern or for other ones, we picked those PCs from EOFs which exactly are taken. We did not invent all of this. We just calculated as most of the papers do for all these models. So that was a little bit of tough work to calculate all these indices for all models, a lot of data crunching. But yeah, so more than, I think, 25 modes we picked.
Okay. Any other? Yeah, your first, second.
Yeah. Thank you, Professor. And I have two questions. The first question is maybe it's basic technical question. Since the climate change, we all acknowledge it, that the mean state of the atmosphere and the ocean may change. So when it comes to the future forecast of maybe the cyclones or the typhoon, for this part, will your method will change the standard and the definition of the extreme events?
Yes and no. Let's say we know that climate change is acting not only on the mean state of the atmosphere and the ocean. We know that climate change is also acting on extremes. We know that the global mean temperature is not the temperature we are living here. We are in Qingdao at one specific day. So that has a temperature. Nobody is living in a global mean. Nobody is living in a time average. Yeah? So these both may change, but this mean is changing because of the system is changing. the system has variability. The variability may change as well, but it means the same physical laws are applied. What we don't know is whether, for example, the PDO will remain more in a positive shift or a negative shift in the future. We know for ENSO, most of the models show a more positive El Nino condition for the future. So for climate change, we have to think twice. We have the change of the background, more El Nino, producing perhaps less cyclones, hurricanes in the North Atlantic as a background. But that's not a direct change of climate change. It's an indirect change of climate change because of the natural variability mode being changed and then influencing the extremes. So you're right, we have to go beyond mean. The mean is not meaningful. The mean is only meaningful if you have to convince decision makers that something is changing, because the mean is something which is to be easily digested. The frequency of a 100-year event, which you did not have observed, or which you do not observe, is a different animal, because you would have to explain to a decision maker that something which could happen more frequently. That's a different explanatory approach. So our study helps to tackle the second point more than the first point. Mean is fine, but these are all extreme events. The top 2%, top 5%. And they are influenced by climate change, yes. Here I showed more or less what we know about the frequency intensity distribution for nowadays. You can approach this for the future as well, but then you have to believe climate models are good. And I showed you that they are good, but not perfect.
Yes, thank you. And my second question is, for your first part, you just use these models to link the extreme densities, the La Nina-like patterns. And I just wonder if it works for other models, like, for CMIP6. Yeah, since a lot of studies, they mention that especially for the future, the RP85, the scenarios, the tropical SST, they show very different trend for observations.
Yes, agreed, but we didn't look at it. For the first part, we just looked so how can we understand what the link is in current climate from La Nina conditions into the North Atlantic for extremes. You're right. If we think climate change, if we would have to inform political decision makers in Europe what the real risk would be, I would be better advised to know my real risk now before I talk something in the future. You know what I mean? Yeah. So assessing the real risk now is a basis, and then you can scrutinize all the climate models, check whether ENSO is in it, whether the teleconnection with DNA is correct, check whether the NO is correct, and then you might perhaps conclude the link is still existing in the model. Perhaps not. We didn't check it in this study, but that would be perhaps a nice PhD topic.
Yeah. Okay. Thank you, Professor.
Okay.
Thanks, Professor Li. Good morning, dear Professor Leckebusch. I'm a PhD student in AFO, and my research is all about East Asia precipitation, especially about high-resolution climate models can capture the capacity. So, could you please turn to the slide 37?
37.
Yeah.
37.
Good that I numbered it. Huh?
Yeah, exactly. My research had do some research about CSM high resolution classification models. We divided the precipitation into each month. Research about signal cycle, and we found that some months the high resolution climate models will enhance the bias, and in some months it will reduce the bias. But you have to do the annual cycle, mostly about decadal variability. So we can see that high climate models rarely reduce the bias. So my question is about because we have researched some about high resolution, but we found that it's a pity that it doesn't improve much more about June JJA precipitation. So now we will try to do something about better convective parameterizations, or just we use some convective permitting climate models will solve these problems. We don't know. Have your team research about this?
Yes and no. The first answer is that's the model of half-monthly basis. So we don't do annual or we do daily precip. Okay, every day we do the precip, and here there is no climate model in it. Okay, that's just reanalysis and observation. Okay, no climate model. So we built a link between large-scale modes from era 5 or reanalysis data, where we assume they're as good as we know, yeah, to regional observations measured rain gauges, yeah, CN 5.1. So no model, okay? The only thing we have here is a statistically guided decision which predictors we use to build the transfer function, okay? Now let me go one more back. So you cannot read this, I cannot read this. That's our target, that's extreme daily precip, and these are our large-scale modes we put in, okay? So that's not a climate model, not a dynamical model, it's a statistical model. Yeah? And these large-scale modes come from reality also on a daily basis. Yeah? We built, to understand this, half-monthly means to make it for a half-monthly time. So we have the intra-seasonal variability in it. The intra-variability is in it, okay? So your second part, high resolution increases the bias. Yo, correct. I would agree with this, but that's from model to model different. Because we don't need this here, you would, in your high resolution model, you would only take the large scale mode and pick this as a predictor, put this in the model, and you would get a better precip than the model itself. That's the idea.
Yeah, thanks.
So perhaps you try this in your high resolution model, whatever. Pick the large scale modes, build such a model, and check whether it's better than the direct model simulation, even at high precision, because then you can save a lot of computing time.
Okay, I see. Thanks, Professor Leckebusch.
You're welcome.
Okay, yeah. The last question, due to time limitation, you are lucky.
Oh, thank you, Professor. Maybe a small question. You have mentioned your CGSM drive a river result, and you showed 4 result is really more similar to the observation. But I want to know, maybe it's different from different. I think is on page.
Wait. Yeah, I think you talk about this one.
Yes.
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 Okay. Yes. For the sake of clarity, we randomly picked these 4 models.
Yeah. Okay.
We have 38. I could show all the 38 models.
Okay.
Yes, but I didn't. Yeah. So that's randomly picked for, yeah, the Norway climate model, MPI. Yeah? So just to see whether the model to model, we have different ensemble members, whether the method still works, and so on.
Yes,
so there are differences for different models. Yes.
Yes, but I was wondering, models with better performance of some climate pattern have better.
Yes. That's similar to the question we had before, because we have biases in 2 ways.
Yeah.
Or the bias in the precips. So let's say this model we picked. Okay, I said we picked randomly. That was not correctly.
Okay.
I show this model because that's a better one. Okay, that has a maximum where we would expect the maximum and does not have the maximum here.
Yes.
Yeah. So I would say this direct precip is more usable than from the other one. One is the Norwegian ESM with low resolution, medium resolution. Yeah. So don't rely too much on this one. It's a thought of theory. It's not that I say this model is good or bad. I don't say this. Yeah? So you will find different biases in all the different models. And you are right. If I would buy modes, before I put them in, as we just discussed, I would expect an increase in the performance as well. Given the fact that, if I think twice, perhaps that doesn't work, because if we bias correct one large-scale mode from one model, it may be not physically consistent with the same model's large-scale mode somewhere else. While if we take the mode as it is, it's at least physically consistent. I would think, after rethinking what we just discussed, that the physically consistent approach is more useful, but that needs to be tested.
Okay. Okay, thank you.
Many thanks. Many thanks.
Okay.
Yes, so there's obviously the long-standing work to tropical cyclone severity, and you have the different categories used in the North Atlantic, category 1, 2, 3, which is based on wind speed as well as MSLP, core pressure. You have in the West Pacific slightly different categorization, at least in naming. Sorry that I go back here. This one is used in the West Pacific. You go from tropical disturbance, tropical storm, severe tropical storm, typhoon, very severe typhoon, violent typhoon, when I could correctly interpret this. And they all have meters per second thresholds. I have to apologize that I don't know exactly the meter per threshold. But what we do, if you remember here, and therefore I put this slide on, perhaps I was too quick. We have a contribution to our severity index, which is based on the wind speed. That's meters per second. So here we have off the coast of Cornwall, 33 meters per second. Yeah? Times 3.6, you get the kilometer per hour. 33 times 3.6, you end up with 115 kilometers per hour. So that's, roughly, if I can calculate. But that's very, very dangerous for land areas. Yeah? If you have 150, 120 kilometers per hour wind speed approaching you. So this value, this real value, meters per second, goes into this value, and then we build the ratio over the percentile, the long-term 98th percentile at this grid cell. This may be, let's say, 20 meters per second. No, that's too high. 12 meters per second, the percentile. So then it gets a value in our SSI, which is plotted here, which is 0.5, something like this, as a relative exceedance of this long-term climatological value. And why do we do this? We assume that people living at this grid cell, well, that's probably wrong. Huh? People don't live in grid cells, but models live in grid cell, but in reality there would be people below it. They will adapt because they know from generation to generation how to build a house at this spot. They will not build a weak structure blown away. So they will have some kind of natural adaptation within a generation, I would say, yeah? Perhaps quicker, but that's also a dangerous climate change discussion. We can have it again. But it means we take the threshold as a percentile per grid cell, and then we assess the potential of damage only above this percentile threshold, which leads you in the end, look at the difference between these two figures. You have high meters per second wind speed here. Brittany, 33, 35 meters per second. North Sea, 33, 35 meters per second. Over land, England, Wales, significant reduction, only 20 meters per second. It's the same storm. And that's because of friction, and the storm slows down over land. But because on climatological average, this value is also lower, we can still then objectively identify where this system has the highest potential for damage. And this gives you this plot. We don't see the difference between the North Sea, land, and this sea anymore. We see the real footprint of potential of damage from this system as it would be getting stronger, 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 strongest over Denmark, North Germany, weaker, weaker, weaker. Here you would say, oh, it does really intensify. No, it does not. Just because climatological, the wind speeds are higher here, here, than here, and here. So with this percentile approach, we bias correct this. The potential of damage would be this footprint. Okay? Welcome. Ugh.
Which attract
I don't know.
more than 15,000.
Oh.
15,000.
Shishe.
Okay. And thank you very much for your excellent talk. And I do think you guys have you are welcome to send an email to.
Yes, please. But not 15,000, please.
Yeah. If you are interested in that, especially.
Yeah. Yes.
Or what?
If you allow me.
Okay.
Professor, thank you for your wonderful presentation. I wanted to know your research showed the extreme event of cyclone and extreme precipitation. Almost every year, same region we found the extreme events. Is there any suggestion from your study other than how to say it? Any suggestion to prevent this event or to avoid the fatalities and the economic losses other than the forecast? Thank you.
Yeah, many thanks for the question. This whole study is exactly about the point, what do we know about the extremity of the event? You cannot prevent the event to happen, but you can prevent impact to happen on the ground by adapting if climate change would increase those events in severity or frequency. Perhaps you may see a change in seasonality of those events. Let's say winter storms in Europe, not peaking in January, but peaking perhaps a little bit earlier. So in November, October, you see perhaps more of those events. That's difficult to prevent the event, but you could then think perhaps differently for a city council, for example. In October, a lot of trees may still have leaves on the tree. So the resistance of this tree may be very much increased. The same wind speed will lead to more damage. So that's obviously a question then to be prepared. Yeah? It's a preparedness. If we don't avoid climate change, then we have to prepare better. We call it adaptation. Yeah? So, and that gives me the opportunity to comment on the previous question with adaptation and climate change. Climate change, anthropogenic climate change, is acting very fast, very rapidly. Nature has normally longer modes. It means that our human ability to adapt and plants and ecological systems to adapt may be overstretched. And that's a real danger because climate change is happening so quickly that adaptation perhaps on natural basis will not do the job, cannot do the job. For building structures, for example, it means we have perhaps to build differently, or we have to build in areas where we didn't build before. We should not build in areas where we should build or build at the moment, you know. So these are questions then to how to translate this information into decision-making to the way that we say, okay, that's potential impact. And therefore, we developed this method to be close to impact and not talking just wind speed, because just wind speed is not the point. The point is this system in the future climate may be more further north or south. Different models give different answers to this. We have uncertainty, so we need more research to understand how anthropogenic climate change may impact on different types of extremes. You're welcome.
Okay, thanks again for George's excellent talk. Thank you very much for your coming. We conclude session now. Thank you very much.
Many thanks.
So we will go to the next.
Yeah.
The room for the cinema.
Yes.
Is this fine? Put the slides on their computer or?
Yeah. It's fine. No, we're fine. Okay.
然后对，可以看一看吧，因为正好评论。